if you open this HDL bits, in that case you will be able to get this website. So here you can see this. So we are having different topics. So if we want to learn Verilog coding, so in that case, if we click on Verilog language, so you can see the corresponding problem set where you can able to practice programming. Okay, there are so many problems which you can able to practice. Problem is nothing but the question, or so many different types of program which you can able to practice. So in this, I'll just show an example of simple wire. If we click on this simple wire, its corresponding theory you can able to get, and then it will also show how the connection is. So here outside the module we have to give input through the input port, and again outside the module we will be collecting the output, but in the module you have to write the design. So since this is a simple wire connection, so what happens when we are going to use only wire connection? So it has been mentioned already, module top has been declared, so which has already declared is present in blue color, and which you want to edit in the program is present in green color. Okay, so here it indicates that already module top has been declared, and one input port and one output port has been declared. The only part that is left out in the program is you have to assign this input for the output. And here you can able to see, that is write your solution, means here you can see that module top definition is there and IO port declaration is there. So what we want to do, we just want to assign out input for the output. So here using the keyword assign, we can able to assign out equals in. Okay, only this statement you have to write, and after writing you just submit, and you can see the corresponding solution. So here you will get the solution. So if it is correct, it will show it as success. Okay, and then here you can see this was the input given for the code to check whether we are getting proper output or not. And here this shows the reference, means for this input it has already predicted that this is the expected output, and yours indicate that what output you have obtained. So here we can see both are same, so as a result there is no mismatch in the result. So you will going to see that your program is success. So like this we can able to write the program and we can able to check whether it is correct or not. So like this we can able to practice. Okay, so whenever you are able to write the program, you can use this window, or you can use this website, and you can able to practice. Not only this wire connection, similarly you are having lot of programs here. For example, if you click on XNOR gate, here it will going to show what is the corresponding circuit or module top it has been declared. Okay, and what is the left out thing. And also one more thing, it doesn't mean that you have to write. See, it has been mentioned an assign statement. So this indicates that only data flow architecture it is considering, and it doesn't mean that always you have to consider data flow only. Here you can write either data flow, behavioral, or gate level. Any type of architecture you can write, and you can submit and check the result, so that you can able to analyze your program writing. So if there is any error, once again you can modify your program and submit. So until you get the correct result, you can able to check whether you are going to get the output properly or not. So like this you can able to practice using this particular website. Okay, so those who are not taken the software or installed the software, you can use this particular website to learn Verilog coding. Okay, if you are having any doubts in this, we can discuss, and otherwise I'll start the corresponding module. So next module what we are having is third module. So in the first module, we just understand the basics like what is HDL, why we use all those things. And in the second module, we have understood how to write the programming in case of Verilog, HDL. And the next one, third module, we are going to consider how to write gate level modeling. Okay, so when we are considering gate level modeling, first we will be discussing regarding what are all the primitive gates that are available in Verilog. So if we know what gates are available and how their behavior is defined, okay, because we should know if I give which combination or what type of input, what output I will be getting. So when we are having that knowledge, then we can use this particular gate while writing gate level modeling. Okay, and also when we are considering a practical gate, so in the simulator you need not necessary to give delay and all, but when I consider the practical gate, every gate will be having its own delay. There will be delay to read the input, and there will be delay to process the given data, and then there will be delay to get the output assigned for the output pin. So the delay may be in terms of nanoseconds or microseconds, which we may not notice. But still, every practical gate will be having its own delay. So what we are going to do means, in this gate level modeling, we will going to assign different types of delays and we will going to observe. So when I introduce delay, whether the code will going to take the delay and whether I'll get the output at a specified time. Okay, why we are analyzing this means, when I download the entire code to implementing the hardware, okay, so there hardware will be having its own delay, isn't it? So I need to get the output at a expected time. If I do not get the output at expected time, then my data will not be processed properly inside the device. Okay, so for that, in order to consider the practical circuit, some delay will be introduced. But while downloading code for the hardware implementation, the delay will not be processed. It will not going to download delay value also, because the hardware circuit delay we cannot exactly define in the program. But what we are going to do, we will going to check whether with this particular delay we are going to get the output means the AND gate. If I consider AND gate IC only, when I give input, it will take around 10 microseconds to give the output means, in the simulation also I should check after giving the input, after 10 microseconds, whether I am getting the correct output. If I am able to get the correct output, then I can download for that to implement. And after implementing, once again, practically I have to check how much delay it is taking. If it is taking more than 10 nanoseconds of or 10 microseconds of delay, that indicates that the actual delay of the device is more, so that we can increase the delay and check. And if it is only for basic gates, then we can easily modify. If I consider a larger circuit like microcontroller circuit or motherboard of the computer, in that so many ICs are there in the motherboard. So the operating frequency of those ICs, all these things we have to consider. If there is any mismatch in the delay, then my data will not be processed properly. We could not able to get the output properly. So to avoid all those things, what we are going to do means, we will introduce some delay and we will going to simulate and check whether after this delay I'm going to get a proper output or not. Okay, to and those things are considered in this module. First, let us understand what are the basic gates available, and then how to give delay and how to check the output or how to analyze the output. Only these things is present in this unit. Okay, so now the first what we are having is, when we are going to consider the logic gates. So in the library there are some predefined gates, so they are called as primitive gates which are already available. We need not necessary to declare that module once again. Okay, and those gates can be divided into two groups. So one is basic gates, that is and or gates, and the another class what we are having is buff or not gate. So one type of classification is and or gates, and the another type is buff or not gates. So in and or gates, these are the different gates that are available in uh, library. So they are and, or, XOR, NAND, NOR, and XNOR. These are the primitive gates which are available. So in all these gates, what is the common thing we have to consider is always the first terminal in the list will be considered as the output, and remain and the other terminals will be treated as input. So if I am considering two input AND gate, in the port list we have to mention one output and two inputs. So always first one will be the output and remaining will be the inputs. If you simply mention four variables, it indicates that that is a three input AND gate, and among that first one will be the output and remaining three are the inputs. So it will going to check how many number of inputs and ports are declared. If in the port list, if there are n number of variables, then the first variable will be the output and remaining n minus 1 variable will be considered as a input. This is common for all these gates. Okay, and the output of a gate is evaluated as soon as one of the input changes. So as I told, if I consider AND gate, there will be at least two input, isn't it? Among those two, either any one or both the input changes, immediately it will execute. So that is what we are going to consider in and or gates. Okay, and these are the corresponding symbols what we are going to consider. So when we are going to consider the basic gates, so the first one is at least two inputs is required, isn't it? So here the symbol is given for only two inputs. If there are n number of inputs, means here the input lines will increase, but output will remain only one. Okay, so this is the symbol of AND, OR, XOR, XNOR, and NOR and NAND gates. So next, let us consider how to use those basic gates. So here we can see the basic gates can be instantiated. So how we can instantiate? By using the keyword. So all the primitive gates should be declared using small letter only. Instead of mentioning and, if you are mentioning it as and in the capital letter, so in that case it will not going to consider this as a primitive gate. It will be considered as a module which you are defining, which the user is defining. Okay, so that is why whenever we have to consider this primitive gates, it should be declared with the small letter keyword, and here instantiation name we are giving, and then we are mentioning, that is always the first one will be the output and remaining will be the inputs. So like this we are going to consider. If there are more inputs, in that case the input list will grow, but output will be always first one. So like this we can able to consider. This is known as gate instantiation. And also one more thing, as I told, these gates are already available in the library, isn't it? So that is why they are considered as primitive gate. So whenever we are considering primitive gate, if we want, we can write instance name, or else we can avoid. Okay, here at the last example you can see I have not used instance name. Okay, since it is a primitive gate, I need not necessary to write the instance name. If we want, we can write. That is also legal. And even though if we skip writing instance name, that is also legal, because what are all the gates that are already present in the library, you need not necessary to create instance, it will only automatically take the instance. Suppose if we write different module, if you want to instantiate user defined module, then instantiation name must be considered, otherwise it's need not necessary. Okay, this is regarding gate instantiation. So that is what I have explained here. So in this first example, always out represents the first port, and remaining ports will going to represent inputs of the gate. And instance name is not mandatory for primitive gates. If you want, you can add, otherwise you need not necessary to consider this. It will and also see here, for 3 input and NAND gate also I have taken the primitive gate NAND, and for 2 input also I have taken the primitive gate NAND. I have not changed. Okay, since for n number of inputs already predefined primitive gate is available, I need not necessary to consider NAND 2, NAND 3, NAND 4 like this to represent how many number of inputs are there. Simply depending upon the port list, it will going to decide whether it has to consider 3 input NAND or 2 input NAND. Okay, like this it is there in the Verilog primitive gate combination. And the next thing what we have to consider is, we should know how these gates will going to behave, isn't it? So when we are going to consider these gates, and we know what are the different values can be given for a gate, either logic 0, logic 1. If we don't know whether it is 0 or 1, then a don't care term X. And if none of the values are connected, then it is a high impedance. Only these four values can be given for the gates. So when these values are considered, how the AND gate will going to behave, that is given in this truth table. So what you can observe, if both the inputs are 0, 0, we will be getting 0. If any one input is 0 and the other input is varying from 0, 1, X as well as Z, output will be 0 only. Okay. If any one input is 0, it will not check the other input. Always the output will be 0. And next, if both the inputs are 1, then the output will be 1. Otherwise, output will depend upon uh, whether the other input is 0 or X. Okay, let us consider input I1 is equal to 1. Then if the input I2 is 0, output is 0. If the input I2 is 1, output is 1. Apart from that, if the input I2 is either X or Z, output will be X only. And you can see in these two truth table, this represents the output and this represents the input, isn't it? So whatever may be the combination, you will not get Z in the output, because it will process the input. Every device will process the input, and according to that it will determine the output. If it is not able to determine the output, it will simply assign X, means unknown. Okay, so it cannot tell high impedance. So that is why for rest of the combination we can able to get the output as unknown. So if both the inputs are unknown, output is also unknown. If both the inputs are high impedance, means if they are not connected, then output is also unknown. It cannot define what is the actual output. So like this we are going to get AND gate behavior. Similarly for NAND gate. So in case of NAND gate, what happens? If any one input is 0, output will be always equal to 1. If both the inputs are high, then only it will be 0. Otherwise, for different combinations of X and Z, we will be getting the output as X only. So like this, we are going to get the output when we are using primitive gate. So this is for 2 input. Similarly, what happens if we are using 3 input? We will be having First, it will going to determine output for two inputs, and then that output is considered as input for another NAND gate. So for example, here how three input is considered means, if this is a three input AND gate, let us consider this is the three input AND gate. So in that case, what it will do means, first it will going to process two input A and B, and this output is taken as a input for another two input NAND AND gate, and then it will going to process. Okay, so as a result, whatever the rules that will apply for two input, according to this truth table, I will be getting output here. If I consider this inputs as A, if I take this particular input as A, okay, so here one input is A and the other input is B and the third input is C. Okay, so in that case, what happens? A will be connected to this port and B will be connected to this one and C will be connected to this one. So output of this A, B will be considered as another signal. Let that signal be equal to D. Okay, so first it will process AB, and then while processing AB, it will take this truth table. So according to the combination of inputs, we'll be getting the output. So that output acts as input for second AND gate. So then once again, it will take two input truth table and it will going to process. So like this, it will going to process. If you are considering 10 input AND gate, similarly in this fashion only, it will going to compute. So if I'm considering 10 input, so then how optimistically I can able to process? Instead of considering one by one separately, I'll be taking 10 5 AND gates parallelly. Okay, so that for one AND gate I can give two input, for another AND gate two input. So like this I can give all the 10 inputs for 5 AND gates. Then output of these two can be given for another one AND gate, and output of these two can be given for another AND gate. So this output will be considered as an input for another AND gate, and output of this will be considered as an input for third AND gate. So like this I can able to process to get the output for 10 input gates. So this is how we are going to consider. Any doubt? So this is how we can able to consider the corresponding AND gate and its truth table. Similarly for NAND gate, and also next what we are having is truth table of OR gate. Here you can observe, if any one input is high, output will be always high, whatever may be the other inputs. And if both the inputs are 0, output is 0. And for different combinations of X and Z, we can see that we will be having only unknown as the output. So it AND gate complement is OR gate complement is NOR gate. So we will be getting truth table for NOR gate like this. Means wherever ones is there in OR gate, we will be getting zeros in the NOR gate. And wherever 0 is there, we will be getting 1. And for X, we will be getting X only. Okay. Similarly for XOR gate behavior and XNOR gate behavior. And next, what type of gates we are having is buff or NOT gate. So why we are considering this buff or NOT gate means, see, whenever we are going to consider a buffer, it will be having only one input, right? We cannot have more than one input, or else we may have tri-state buffer, means we can have a control to turn on the buffer or to turn off the buffer. But there will be only one input for a buffer. And similarly for NOT gate, again, it is also having only one input, isn't it? So these buffers are different from AND OR gates, because for AND OR gates, we will be having only one output. But for buffers or NOT gate, we will be having only one input. That is the difference. And for AND OR gates, we can have n number of inputs, and for buffers also we can have more than one output. Okay, so that is the difference between not buff non or not gate as well as and or gates. Okay, and these are the corresponding symbols we are going to use: input and the out. And symbol of the not gate, it is similar to buffer, but we are having a small bubble which will going to reverse, I mean negate the corresponding input. Okay, and here what we can observe is, if there are more number of variables in the port list, so what happens, always the last terminal in the port list is considered as a input. Okay, so in and or gate also, first we will be having output and then we will be having input. Okay, inputs. But here also first we are having outputs and then at the end we are having input. Okay, that is the difference. You have to carefully understand between and or gates and buffer not gate. And here this is one of the example. Here we can see how we can able to instantiate the buffer. So when we are going to consider buffer, there will be no change in the output. Output and input are same. Then why we want to use the buffer means, if the input signal strength is less, it will be enhanced. Okay. So what is the main application of this buffer means, for example, if I am going to consider this particular buffer is driven from the AND gate output. Okay, so when we are considering AND gate and that output is connected to the buffer, and these gates, let us consider a 2 input AND gate with the input A as well as B, and this is the corresponding output Y what we are having, and then here we are having the intermediate output C. Okay, so if the output of the AND gate is logic 1, so when the output of the AND gate is logic 1, how the buffer will going to recognize the output? If the corresponding input voltage for the buffer is between the range around 3.5 to 5 volts. Okay, so in such case, the whatever the value of C, that will be treated as logic 1. For logic 0, it will going to consider the values from 0 volts to around 2.5 volts. So let us consider these are the corresponding valid voltage levels for logic high as well as logic 0. Okay, so in that case what happens, if the signal, if the value of C or the voltage at the port C is equal to around 3.5 volts, then it is read as logic 1, but the output Y will be having the voltage nearly or approximately equal to 5 volts. So now the strength of the signal from 3.5 volts to 5 volts is enhanced. Even the output is equal to 1 only. Input is also 1, output is also 1, but the strength of the signal is increased. Why we want to consider this means, if an AND gate is driving more than one particular circuit. Okay, so what happens, according to that, there will be a current will going to divide. Current will be divided into two paths, isn't it? So even though the voltage between the output terminal and ground remains constant, the current flowing from the output terminal will be divided into two paths. And we know that voltage will be equal to current into the corresponding resistance present in the wire. So if the strength of this is less, then it cannot drive more number of gates properly. Instead of connecting directly the output of AND gate to different devices, we can connect it to the buffer. It will increase the signal strength, and then this can be given as an input for some other circuit. Okay, so that is the reason why we are going to use buffers. Okay, so this is how we are going to consider the application of buffer. And here, though the input and output are same, the main advantage is we need to increase the signal strength. Okay, and in case of inverter, what we are going to do, if the input is 1, we have want to negate, we need the output as 0. So in such case, we are going to use NOT gate. And this is how we can able to instantiate either, see, always the first will be the output and the last will be the input. If there is only one output, we can write it as, we can represent 2 ports in the port list. If we are mentioning 3 ports, in that case, it will treat first 2 as output ports and last one as input port. This is the difference. So if I consider similarly, I'll just show the difference between AND OR gate. So if I consider AND gate, in that case, I will be having out, and then I will be having input 1, input 2, input 3. So like this we are going to consider. Okay, and here also we can see the output port and first output port and then input port. Here also first output and then input. But the thing is, in case of AND OR gate, only one output and many inputs. But in case of buffer or NOT gate, many outputs and only one input. So like this, we are going to consider the difference between buffer as well as AND OR gate. The same thing holds good with respect to NOT and AND OR gate. Okay, so like this, we are going to consider the corresponding gate types. And the truth table of this buffer and NOT gate is as follows. So here, if the input is 0, output is 0. If the input is 1, output is 1. Because buffer will not going to change the value. It will simply enhance the strength of the signal. And in case of NOT gate, if the input is 0, output is 1. If the input is 1, output is 0. But if the input is unknown or high impedance, it cannot predict the output. So always output will be equal to unknown, both in case of buffer as well as in case of NOT gate. Okay, this is how we are going to consider primitive gates. So till now, whatever we discussed regarding AND OR gates as well as buffer and NOT gate. And the main difference between them is, in case of AND OR gates, we can have only one input and in case of AND OR gate, we can have only one output and many inputs. But in case of buffers, we can have one input and many outputs. Okay, so this is what we are going to consider. And always, in case of AND OR gates, first port will be the output port. And in case of buffer gate, always last port will be the input port. Remaining will be the output ports. These are the main difference between them. Okay. And again, in case of buffer as well as NOT, we are having one more option. Means sometimes we have heard regarding tri-state buffer and all. So what this tri-state buffer and all it indicates means, if we want to enable the buffer whenever it is required, I can give enable, that is the control pin, and then I can enable the buffer, or else I can disable the buffer. Similarly for AND gate also, NOT gate also. We are not having that type of control in AND OR gates, but we are having enabling and disabling facility for buffer and NOT gate. So again, if I want to enable or disable, again we have to consider, either we have to consider positive, that is positive logic or negative logic. Positive logic means if the control is 1, it will enable. If the control is 0, it will disable. Negative logic means if the control is 1, it will disable. If the control is 0, it will enable. So like this, depending upon whether we are using logic high enable or logic low enable, we are going to consider buffif 1 and buffif 0. Similarly for NOT gate, not if 1 and not if 0. So like this we are going to consider. And the next, this is the corresponding circuit for that, symbol for that. So here we can see input, output, and here we are having a control logic or control input. Okay. And how it will going to work means, let us consider this truth table. So here, if I am considering buff if 1, so in that case what it indicates, when the control is high, in that case whatever the input is there, we will be getting the same output, isn't it? So here, if the input is 0, output is 0. If the input is 1, output is 1. If the input is unknown, output is unknown. Here also, if the input is Z, output will be unknown. It cannot be Z. But when the control is 0, so here what happens? In the truth table, you can see the output as 0. So what it indicates means, it will inactivate the device. If the device is inactivated means, it is not considered. Even though if it is present in the circuit, it is not considered for processing. So as a result, it will be treated as no connection for the further circuits. So it will be giving the output as Z. Okay. If there is a connection, either it should give the input as logic 0 or logic 1. If there is no connection, it cannot give the input as either 0 or 1. So it will inform that as no connection in terms of giving the value as Z. Okay. And here, if it is not 0, instead of that, if the control value is unknown, then here you can see L. If the input is 0, it indicates L. If the input is 1, it will indicate H. So what this represents means, this is not actually 0. This represents weak low. So we know the signal strength, isn't it? So when we are getting signal from the supply, the strength will be maximum. When we are getting signal from any other output of the gate, then the signal strength will be medium. And similarly, we can have low signal strength. Since the control itself is unknown, then in that case, a low logic 0 will be considered if the input is 0, or weak logic 0 is taken. And similarly, here weak logic 1 is taken when the control is unknown. The same thing happens if the control pin is not connected. So it will not going to disconnect from the circuit. It will just give weak values. The strength of the signal will be reduced. Okay. This is how we are going to consider.